All right, welcome everybody. Happy Halloween, and we have a special Halloween seminar today. Big thanks, I've already thanked her many times to everybody because I'm bragging about it, but big thanks to Neely for putting together our Halloween snacks and a Neely designed and executed bubbling cauldron. So fantastic, Neely, thank you. Yes, you can applaud for that. That was... Thank you so much. So it is my great pleasure today to introduce today's speaker. It is Dr. Mayra I Oyola-Merced, who is a professor at the Department of Atmospheric and Oceanic Sciences at the University of Wisconsin-Madison. All right. So you have one fan. Okay. And she's also affiliated with the Center for Climatic Research at the Nelson Institute for Environmental Studies. She, before becoming a professor, did many, many things. I'm just going to mention, I think one of her most recent positions was working as an atmospheric and ionospheric scientist and deputy director at the International GNSS Service, which is at NASA JPL. But she's worked many places, National Weather Service, NRL, et cetera, et cetera. Mayra got her PhD in atmospheric sciences from Howard University. And she has a lot of service that she does. She's on the National Academy's Committee on Earth Science and Applications from Space Board. She's also on the UCAR Members Committee. She also chair of the AMS Women's Committee. And she also does a lot of work in improving inclusivity in our community. And that includes serving on the AMS Board of Representation, Accessibility, Inclusion, and Diversity, or BRAID. And I want to thank Mayra for all her wonderful work. And I'm excited to hear about her wonderful research. So take it away, Mayra.
Thank you. So happy Halloween to everyone. Let me check. Testing. Okay, good. So happy Halloween to everyone, and thank you for that introduction. I am Mayra I Oyola-Merced, so I'm going to start to talk a little bit about myself. I don't like to talk about myself, but I have a very unique path, so I want you to understand where I'm coming from in terms of my research. So, as I was mentioned, I am an assistant professor at the University of Wisconsin-Madison. I am originally from Puerto Rico, so I decided to study atmospheric sciences because of a mistake. I'm a theoretical physicist as an undergrad. I had that as an undergrad. And I wanted to take an astronomy class, and I forgot to enroll on the class on time. So I ended up taking Meteorology 101 as a class just as a curiosity. I was curious about that, especially because, as you well know, Puerto Rico is impacted by severe weather and hurricanes. So I ended up falling in love with atmospheric sciences, and I continued that path towards grad school. Unlike many people that come from my background, I don't do hurricanes, but I've always been intrigued about the impacts of aerosols. These tiny little particles are suspended in the atmosphere and severe weather, and hurricane is one of them. So I have this here, not because I want to talk about this research, but it is the shameless plug that we just had a paper that came out looking at my background in dust and utilizing observations from CPEX in terms of the radiative transfer. And I'll explain a lot more on this, but applicable to what we're going to talk today. And as I mentioned, aerosols are my one true love. I had the amazing opportunity to spend a lot of time at sea when I was at Howard University. I think I have over 200 days at sea, so the oceanographers at AOS at EW make fun of me because I have more time than them. And the word sea is actually on my dissertation. But yes, it was a great time. And so from there, I started working with weather modeling and a lot of satellite remote sensing. So my path has gone from doing dust radiance modeling in grad school to doing a little bit of data simulation and radiation at NRL, to do satellite retrievals at JPL. So now I'm kind of an expert in reading in between the lines and connecting dots. So my research group kind of reflects that. And my research group at UW is the satellite observations for aviation, radiation, and severe weather, or SOARs, not to get confused with UCAR or in-car SOARs. And these are the 4 areas that we focus on. Aerosols are my main love. However, I have a little affair with aviation. But today I'm not going to talk about that. We're going to be focusing on these aerosol radiative impacts and also how aerosols can affect severe weather and climate. But I wouldn't be able to do this work if it wasn't for my research group. So I just wanted to give them a shout out. So my grad students, my undergrads, and I have other students that are now on their first year that have joined the group from different departments. So I'm very grateful for their contributions to this presentation, and I'm going to start now talking about wildfire smoke. So as we know, wildfire activity is on the rise, and I mentioned I was from Puerto Rico, but I spent 8 years in California. So you can only imagine, I can tell you lots of experiences about actually exiting the Sierras when a wildfire started, to almost having to evacuate my home. And I know some of you have experienced that here as well. So here I'm showing this 1996 to 2016 maximum annual burnt area figure, along with the monthly burnt area time series for different parts of the world. This was published in Nature in 2022. We can see that there are many areas of the world that are suffering and that are experience wildfire activity. Of course, we focus here in the U.S. Because this is where we live and the place that we call home. So when we think about wildfire, the first thing that comes into mind is pollution. And for the general public, this concept of particulate matter, PM 2.5 or PM 10, is something really important. And we know that as we move forward, there's going to be future implications in terms of wildfire activity in the United States, because the hotter it gets, the more wildfires we're going to have, and the more pollution we're going to have. And that has certain implications in terms of health, social inequities, and economic impacts. However, that's not all. So when we talk about wildfire, we normally focus on the regions around the world where we see these source regions, and of course we think about life property first, and then air quality, immediate air quality impacts to health. But there's some transport, and there's some transport of this downwind to other areas. You probably can remember last year in 2023 where we had that massive advection from Canadian wildfires, and that specifically affected the Midwest. But it is not just air quality what we have to consider. And I bring this because in Wisconsin, where I now call home, we have the perception that we have clear air quality, which is good. It's true, we do. And as an example here for that, I have this image or this plot which depicts fire radiated power from MODIS. And it's basically some radiated power over the years of 2000 and 2023. So it's how intense those fires are over that period. And what we see here is not a surprise. We see a lot of activity on the West Coast, Canada, and of course, if you know about wildfires, you know that there is a wildfire season in the southeast of the U.S., especially early in the year. So when it comes from the standpoint of wildfire locations, we don't think about the Midwest. There are wildfires here and there, but it's not a major issue. However, we need to think about the advection. And again, just for context, in Wisconsin, most people do not realize that we get a lot of advection of wildfire smoke, and we realize this actually doing research. It's not something that's commonly known. So I moved to Wisconsin in 2022, and again, first thing that I noticed was the color of the sky. And for a lot of people, of course, you see these beautiful colors and you get excited because it's a beautiful photo opportunity. But in reality, that's, for a trained person, when I looked at that, I immediately think aerosols. So there's aerosols in the atmosphere. This is a particular first time that I saw a strong aerosol advection over Wisconsin. That was between September 10 and 15 of 2022. As a matter of fact, our forecast at that point said that we were not going to have much rain, and we had floodings that day in those 3 days. And I added the last one, even though it's not from September, and it was something that happened afterwards. And at that point, we were very sure that there was a lot of advection of wildfire smoke. But it's extremely cool to see just the reaction, my reaction, but also lightning generated during that time. Okay, so wildfires are affecting us downwind. And so when I realized, okay, there might be wildfire here, let me go to the literature as a good scientist I am. So I found this paper by Sang et al. Published in PNAS in 2022. And they had this beautiful modeling experiment where they are looking at the impact specifically of wildfire smoke from California. And they focus on the 2020 season, which was a very strong one, and how that impacts precipitation and precipitation rates over the continent of the central United States. So one of the things that they found was that Western U.S. wildfires may increase heavy precipitation rates by 38%, and also that it impacts the production or the size of hail. So they observe significant severe hail or hail larger than 2 inches might increase by 34%. However, there's the suggestion that wildfire smoke may suppress precipitation, and we know that there's a combination of different factors here. Some factors are associated with thermodynamics, others with the cloud physics, particularly how these particles can enhance or deplete moisture, how they can enhance wind shear, and also storm relative helicity in the central U.S. The second study that we found, so there are not many, but this one is extremely impactful, at least in my opinion. It's a paper that was published in 2014. I was still in grad school then. And here, they're studying the 2011 tornado outbreak. The importance of this study is that it's the first time that smoke severity is used to understand tornado development. And the reason why was that it was hard to have aerosols in model back in 2011 or 2014. So they studied, I believe it's 2 days. They looked at there might be issues associated with smoke aerosols, heating, increasing the surface heating and increasing CAPE, which in turn enhances atmospheric instability, and that favors tornadoes. They found a relationship in terms of enhanced wind shear, as well as, again, the aspect that we talked about. Depending on the conditions, aerosols may be responsible for dampening or enhancing some of these conditions. And just if you are not aware of the 2011 tornado outbreak, here are some statistics and some figures. As a matter of fact, just so you're aware, there were 360 tornadoes reported, 324 plus fatalities, a lot of injuries, and a lot of damage. So something extremely sad in terms of this, but scientifically interesting. So this 2011 tornado outbreak is going to be one of the starting points for our research. So I want to talk a little bit more about aerosols. Probably this crowd knows a lot about this, but just as a quick reminder, in terms of radiation, aerosols have the ability to scatter solar radiation. We have incoming solar radiation. Of course, if we have smaller scattering aerosols, they're going to be responsible for sending that energy back to space. On the other hand, when we're talking about something like wildfire smoke, here we go. We get this wildfire activity. Depending on the intensity and fire conditions, we're going to get some of those aerosols aloft. A particular source of, or a byproduct of wildfire aerosols is black carbon, and by the word, it's black, so it's absorbing. And so a lot of that energy or solar radiation gets absorbed within that particular aerosol cloud, and then it gets evicted to other places. So why is that important? It's important because aerosols affect the distribution of temperature in the atmosphere. So more often than not, we see aerosols in terms of AOD or columnar averages, but it's extremely important to know the vertical distribution, which is one of the biggest challenges that we have as a community right now, is to understand where that aerosol is located and why. Well, here we have an example of a clean atmosphere to get your solar radiation, incoming solar radiation. If you have nowhere, you always have some aerosols, so if you have a small amount of aerosols, you may get some weak heating. But on the other hand, if you have aerosols located in different portions of the atmosphere, such as in the center case where we have haze, or in the case on the right, which is dust, what we can see is that those aerosols can absorb or enhance the heating at different levels. And it depends on the type of aerosol, its chemical composition, the age of the aerosol, but also the height and the distribution. So for example, in a case like this, we see heating across the lower portion of the atmosphere, whereas in the other case where the aerosol is a little bit higher and we're talking about dust, which tends to be an absorbing larger particle, what it's doing is warming the atmosphere, what is cooling below. So technically there's stability at those levels that may tamper with the formation of any type of weather. So let's go back into the 2011 tornado outbreak. We know from literature, we know from my eye observations that it's possible to have aerosols and that those aerosols can have an impact on weather. However, about the Midwest, one of the biggest questions that we had was in terms of how often does this happen? And are cases like the 2011 or the September 2022 rare occurrences, or is that more common than what we think? So we started to look at the 2011 outbreak, and because there's literature, there's things for us to compare, and the first thing that we did was to actually take advantage of reanalysis data, and the reason why is because we now have this very long data set that we can go back in time. So we're using for this Mayra I aerosol and also associated pressure, temperature, humidity, and other atmospheric parameters. This is 3-hourly gridded data, and particularly the part that we're interested is in the vertical profile. And in terms of aerosol, again, I'm focusing here on black carbon. For the rest of the presentation, this is all going to be black carbon. We looked at other things like organic carbon and other species. But with this was applied for, it was one of the tools that we applied to assess the aerosol impact on weather conditions. The other one was NOAA's SPC severe weather reports, because we had information as to where in time and space these severe weather events were happening. Particularly, we're using daily reports of tornado and hail. There's also wind information that we don't get to use, at least not now at this portion of the research. But it's easy because we have our lat longs and we can collocate with Mayra aerosol and PTQ. And to confirm that there was severe weather, we're using satellite data, particularly NASA iMerge, which is a satellite-based estimate that uses microwave, GPM, and TRIM, depending on the year, and also infrared satellites to obtain rainfall estimates around the globe. And this data comes every 30 minutes or every 3 hours or daily, so we have different options for data to use. So again, this is used to correlate with aerosol concentrations and understand where those severe weather precipitation patterns were occurring. So here we start, and we see here this particular case during the tornado outbreak. We start in April 25th of 2011. We see here some advection of biomass burning, or associated with black carbon associated with biomass burning, coming from the Yucatan Peninsula. The white dots are the hail reports or hail locations. The red are tornadoes, And maybe you can't see it well, but we actually used to plot the radar colors here, and some people have a very hard time looking at the colors, so we changed them. But that's precipitation, so the darker the color, the heavier the precipitation is. Likewise with the aerosol, darker aerosol, more concentration. So we look at a couple of days first, and if you notice, the severe weather kind of follows the aerosol plume. We got curious now that we had the data, and we ended up running the entire month. And likewise, we started seeing patterns. And you can see on the top the day, and again, white is hail, red tornado activity. Again, we're using SPC reports. They're not perfect. Sometimes there might be severe weather somewhere else, and it's not captured by that because a lot of them rely on either radar or people reports or National Weather Service forecasters. But it's a pretty good indicator, and now we're seeing that there's some relationship between those, right? So we kept on looking at many of these cases. As a matter of fact, many cases we ended up covering over 20 years of daily reanalysis. So, and we saw the pattern over and over again. So other than just getting really excited and starting yelling in my office, oh, this is really cool, we started building a climatology using reanalysis data. And the first type of climatology that I'm going to show here is just focus on the aerosol itself and how that aerosol relates specifically to the Midwest. So the focus again is on black carbon, but as I mentioned before, we also evaluated other constituents. So again, we rely on Mayra. Yes, I'm not using ERA or using WF data. I work for NASA, I'm a little biased. And I also have reason to believe that the actual aerosol reanalysis is really good. So using black carbon concentration, this is the resolution, and again, we focused on black carbon numerical profiles, although, however, what you're going to see here, it's more the graphical or geographical distribution of these aerosols. So this is a 43-year climatology of black carbon, and this is black carbon at the surface. And I am not showing the winter months or the later months of the year. I want to focus during this particular months over here. But as we can see, we see some of these surface mass concentration areas are very prominent. And in here we can see April, May, June, and that's where associated to the wildfire season in Canada. We see here July, August, and then when we go to actually August, we see particularly that also Canadian and West Coast wildfire activity. But we don't see much, right, when it comes to the Midwest. So we're looking now into not just specifically focusing at the surface, using surface mass concentration, but also looking at the column mass density, which implies transport. And this is where things get really interesting because we can see the activity, how that activity affects areas of the Midwest and the East Coast of the US. And again, we see source regions, that very consistent wildfire activity from the Yucatan Peninsula and actually from South America as well. We see here, again, the Canadian wildfire season, and as the West Coast season also starts or begins or it gets stronger. So there are patterns that now for us, we were really interested in understanding now how is this related to the actual formation of severe weather in the Midwest. So we went from weather to climate. I'm going to bring you back to weather. And we've seen this plot before. So a couple of the questions that we had, or a couple of points that we have now covered. We learned that there is a climatology associated to these outflows. It's probably more common than widely recognized. The literature does suggest that these events have increased and that will continue to increase in the future. And the question for us is how do we learn more about the impacts on severe weather? So again, we have some tools at our disposal. We know that when it comes to aerosols and precipitation, there are three things that we need to consider: thermodynamics, radiation, and cloud physics. For the remainder of this presentation, I'm going to focus on thermodynamics and radiation. While cloud physics is something that we started to touch upon, it's a very difficult problem, and that's part of the reason why I'm presenting here, to see if I can find more collaborators and people interested in doing this. So here we have our SPC reports. So the question also is, how many of these SPC reports include aerosol? And so we went ahead and downloaded, Stephanie, who's here, went ahead and downloaded over 20 years of SPC reports. And what we ended up doing was actually kind of quantifying how many of these actually contain aerosol. Is this really relevant? So that's the first question. So, let me go back. One thing is that we're using, again, mostly data from the severe weather season in the Midwest. So 1st March to June 30th. Severe weather season now, it's a little bit questionable because we're getting a lot of severe weather in the July, August, and even now. But for the purposes of this study, this is where most of the data was analyzed. And here are some of those results. And it looks a little bit complicated. Follow me here. What we have here is the last 14 years. I'm plotting only from 2010 to 2024. And what we see here are the grayish are the total SPC reports for that particular season. And if you look at the numbers in here, we're talking about numbers in the thousands. The red is air cases where there's no aerosol. And then the blue indicates aerosol. And for the most part, we have obviously more cases with no aerosol than with aerosol, but the percentage, which is on the right side, is actually high. So it's anything between 30 to 40%, with an exception, very clear exception, which was 2011. And then the other particular case that is very interesting is last year, 2023. So, again, what else do we want to know is that since now we have this information, can we use these aerosol-laden profiles and extract thermodynamics and the aerosol profiles for each one of these cases? And yes, we can. And if you were yesterday at Steph's happy hour talk, you probably remember this graphic, where one of the biggest things that we have for thermodynamics is SQTs. And I am a thermodynamic professor, so I'm teaching about this all the time. So this is an example for a tornado event on June 1st, 2024. But again, if we go back and you see the counts here, in the thousands, that's how many SQTs we have for those aerosol cases. And we're focusing now in particular parameters that may be associated with the influence of aerosol. So one is CAPE, or Convective Available Potential Energy, or the amount of energy available for convection, at least in the mid-latitudes. I know people that do tropics, we can talk about that. But in the, we are filtering here we're removing all the low CAPE. So basically all CAPE less than 500 is removed, and we're hoping to find really high CAPE or not very low, and that was part of the algorithm categorization. This is a case where we have a lot of CAPE. The other thing is LCL, because low LCLs are normally associated with severe weather formation. This is an example where, again, LCL is about 300 meters. And then SIN, which is that energy that it must be overcome for an air parcel to rise and to initiate convection. So we want very low CAPE. And again, this is an example where you have that as well. Now, and one more thing that's in here that's not a traditional SQT thing is the aerosol profile. And again, we're looking specifically not only the aerosol distribution throughout, but where is the aerosol peaking, because that is going to have an impact on the actual thermodynamics. And if you recall from that plot, that's what we're after. So let's go a little bit into, gonna go straight to methodology. Again, Mayra II reanalysis. We calculated Cape, scene, and LCL conditions to ensure severe weather cases were included. And we calculated correlations and also trend lines and regressions for all of these cases. One thing that I do not recall mentioning before is the aerosol. All the aerosol models, they have aerosol all the time. So we have to remove some of that background. And I want to make that note that the background aerosol was actually removed from the reanalysis. Now I'm going to go through a couple of years here and show you some data or some of the results. And as I mentioned, 3 parameters of importance for us, LCL. Here you go. So here we have the relationship of integrated aerosol and LCL in meters. And one thing that I want you to notice here is that the integrated aerosol in these particular cases is different. So we can see here that values of integrated aerosol can go to 2, 1 to the minus 8. In this particular case for hail, we notice that there's a tendency to find higher aerosol or integrated aerosol when you're dealing with hail cases. But here we didn't see much in terms of the LCL. So that was kind of a bummer when you have the hypothesis. But then we looked into the Cape. And this is interesting because when it comes to Cape, we have seen this particular behavior through all the data set. We have broken this down in regions, and we have broken this down by event, by year, and there's always an increasing trend. So again, integrated aerosol and Cape. So in other words, higher Cape, lower aerosol associated with lower Cape, higher aerosol, integrated aerosol associated with higher Cape. And the trend seems to be higher for hail compared to actual tornadoes. So this in here is the position of the aerosol. And again, there's the SQT right there, so you remember why it's that important. But here we have the actual, on the y-axis, there are maximum aerosol pressure. So where in the atmosphere is that aerosol, the maximum layer of the aerosol is located. And again, when it comes to LCL, we don't see much. But when it comes to things like Cape, here we see the higher Cape values for both tend to associated with a lower aerosol peak position. So again, this is 2011. Out of curiosity, here's last year, and we come to talk about LCL issues again, and we see that there's not much change here. However, one thing that I want to mention with this particular case is that obviously there's a lot more aerosol, and that's why I'm signaling to these blue boxes here compared to 2011. And just moving forward for that particular 2023 case, again, in terms of K, we see the same tendency. But where it gets really interesting here actually is in the outliers. And what we see here, for example, that there are some of these outliers that are associated with a lot of aerosol in the cone, and they tend to be aligned with lower K values. And likewise, when it comes to hail, we see that. And here, I want to make the caveat too, that we see that some of these dots have different colors, green, red, and blue. So that refers to the height of the aerosol in the atmosphere for reference. So we can see that mostly aerosol, low aerosol, and mid-level aerosol, so basically aerosol between 700 hectopascals and 900 hectopascal or lower, tend to be in this category of outliers. So there's a potential that the aerosol is so heavy that it's just reducing Cape in those particular circumstances. Now, Here we see that behavior again. In terms of LCL, it's pretty flat. However, likewise, we see, particularly with the outliers in here, a pattern that's interesting. And I want to point out that in here, in the y-axis, we have the hectopascals, or basically the levels of the atmosphere. And we see a lot more cases in terms of hail that are associated, where we find aerosol layers higher up. So that's another thing that it's really important in terms of trying to understand how the position and the concentration of aerosols may impact our thermodynamics. Okay, so I'm gonna move forward and talk a little bit more about that 2023 case. And if you notice, there's a lot of aerosol. You probably were paying attention to the news. It was basically all the United States was covered by this type of smoke. And particularly why I bring this up is because I've talked about the relationship of aerosol and convection and severe weather, but the opposite could be true. And we had this situation in Wisconsin last year. And so far, we've used a lot of reanalysis, which is, obviously, it has some limitations in terms of understanding, in terms of resolution, in terms of where the aerosol, how good is that aerosol profile. But the benefit that we have at UW-Madison is that we also have instrumentation in our roof. So with that in mind, I'm going to show you a study case from summer of 2023. And this is actually the same view that I have from my office. And as a matter of fact, there's aerosol here. This is the beginning of that wildfire event. And this is probably one of the worst days of that event in Wisconsin. As a matter of fact, we broke all records of air quality. But the interesting fact was also the forecast. So based on her and based on the National Weather Service, that was our forecast for the 27th of June of 2023. Same thing happened on the 28th, where we were actually supposed to see severe weather and high precipitation. The forecast had us in the mid-80s. The actual high that day was around 80, and we didn't see anything. So we are obviously seeing a case here where we are studying precipitation suppression, and we don't know if it's by cloud physics or radiation, but we have the potential to understand what's happening. During that day, we had a couple of flights out of Madison with very poor visibility. So we know from reports from pilots' reports out of MSN, that aerosol layer was close to 10 kilometers or higher. But again, as I mentioned before, the benefit that we have is that in our building, if you have never been to Madison, this is the Atmospheric and Oceanic Sciences building. It's the birthplace of satellite meteorology, and we also have a lot of instrumentation in the roof, as I mentioned before. But one of the things is that we have the HSRL, which stands by High Spectral Resolution LiDAR. And that figure on the right is actually a depiction of the HSRL during the month of June of 2023. And if you take a look at the last portion of the month, we're going to notice that there's a lot of aerosol distributed along the entire atmospheric column. These observations are observations of backscatter that we can change into extinction. And I'm not going to go through the math of doing that, but we can utilize extinction to then run radiative transfer and understand not only the distribution of the aerosol, but what the impact of that aerosol is through those days. So a little background on what we are going after. Technically speaking, this is what we need to solve. We're trying to look for heating rates, and the best way to do that is to actually look at a radiative transfer model. And what we want to do again is look at the rate at which the temperature of the air changes with respect to time or altitude. Now, we use an RTM to do the calculation of heating rates. Specifically, we use Fouliagou to do this. And we did it for those final days of the month of June where the forecasts were pretty bad, and we also had a lot of aerosol in the atmosphere, poor air quality. So this is what we see here. Again, mean heating rates or the warming that we had during that time from 25th to 30th June of 2023 in Madison, Wisconsin. Basically what we have here is the difference between runs that were done considering aerosol from HSRL and others that were not considering the aerosol impact. And what we have here is the difference of that. So how much heating was associated to the presence of aerosol. And this is in the shortwave, this is in the infrared, and then at the end we have the total heating. The infrared line looks like one. In reality, is that basically the calculation is the same. So apparently the aerosol wasn't active, at least with the properties that we used in the infrared. But in terms of shortwave heating, we can see how that shortwave heating is distributed throughout the entire day, and there's a lot of heating. So basically what's happening is we have, this doesn't include the surface, so this is above 900 hectopascals and above. So what we see here is a consistent warming of that atmospheric layer all the way throughout to 100 hectopascals or lower. And this is specifically important because this is what numerical weather prediction models sometimes tend to have problems with. Now, another thing that we are working at, as I mentioned before, is looking at the relationship of precipitation and aerosol. And we just started doing this, so I just want to show you an example of how does that look. And how we do this right now is using satellite remote sensing, particularly GPM, or using a KU band from GPM. And this actually was from this year. We had a severe weather event on July 15, and the limitation with this is the overpasses, so we don't have overpasses all the time. So particularly here in the Midwest, we had an overpass at 6 UTC and another one at 21 UTC that captured that beautiful heavy precipitation. And again, what we're trying to do, and I have a new grad student working on this, is looking at the relationship of that aerosol as it moves or is there before the precipitation gets there, and what that does into the atmosphere. Interestingly, in this case, we see heavy precipitation between these latitudes, close to us. And then again, we see the aerosol much higher in the early morning and then lower, but still the heavy load of aerosol is between latitudes 42 and 44. So we see a change on that distribution over that day. Again, this is just to give you a little bit of taste of what the direction that we're going after, but something to take into consideration if someone's interested in collaborating on this. Now, I'm going to wrap up by just showing a little bit of a result that we have from machine learning. And the reason why I decided to do this at the end is because it kind of summarizes one point that I want to make. And well, I'm not going to go into the details of the model. Just very quickly, we trained it with Mayra, and again, we're using black carbon concentration and wind speed, temperature, and atmospheric parameters. And we're using CNN and LSTM because we found that that combination of hybrid CNN and LSTM actually works better for our forecast. What I want to say here is that it seems that these wildfire events are not going to go anywhere. As a matter of fact, what I'm showing here is the 2035 forecast, and to that we subtract the mean of the climatology that we had. And we're looking to see if there's a decrease or the areas in which we find decrease of black carbon. And here we have our suspects. So obviously we see high numbers around California and obviously Canada. But what I want you to pay attention to is the actual values. we're talking about numbers over 400%. And when I looked at the climatology, not only the machine learning model, but looking into the climatology of this, the numbers were consistent with what we have seen over the last 10 years. So this is a problem. And I'm focusing again on the Midwest. And while here, the colors that overpower the entire graphic are the big dark reds, if you look at the Midwest, we still are seeing something between 100 and 200%. So that's quite concerning. So future steps, so we can have some time for questions. What did my, all right, I lost my cursor. All right, let's see. Okay. Again, some of the ongoing work, we're using GPM data to analyze a KU band from GPM in smoke-affected convection. We want to continue doing LiDAR experiments. The one that I showed here is in a non-convective environment, but some of the other studies that we're doing are actually timing the HSRL observations before and after the event, just to look at the changes throughout a severe weather event, because the HSRL doesn't operate during rain. So, but that's one way to go about it. Same with looking at radiative transfer, trying to understand more how we can improve radiative transfer and how we can better represent aerosols. Couple modeling, my students know that every time that I talk about this, I mention we need a model. We need a model because we can do all of these observational studies and we can do radiative transfer, but ultimately what we want to see is the relationship of that aerosol with the dynamics, and that's extremely important. And we will continue working with machine learning and, of course, assessing the long-term effects of smoke on regional weather. Now, since it's Halloween, and I'm not dressed up, I thought about bringing my tornado costume. The best thing I can do is actually show you a reel from last year featuring some of our AOS professors. So I hope all of you have seen Twister or Twisters, either one of them. So I leave you with this. He was actually teaching for real when we sneaked into his classroom. All right, thank you so much.
Yeah, thanks so much, Mayra. That was terrific. Lots of questions. So let's get started.
Hi, Myra. Very, very nice. You very convincingly showed that 30 to 40% of severe weather outbreaks have aerosol in them. But can you go beyond that and say that the aerosol increased the chance of severe weather on those days?
That's why we need the modeling part. So and I understand that there's a correlation does not mean causation. So I'm showing a lot of correlations here. But I think that's an important first step in acknowledging that this is happening. But yes, as we've talked during this entire week, I need your support to be able to look deeper into this. Yes.
Sorry, I pretty much had the same question. Yeah.
All right, I walked over here. Should have gone the other way. So, here we go. Next, and then I'll take back to the front row here. You help pass this back.
Hey, Mayra. I'm a UW alum, so go Badgers.
Yeah.
Yeah.
On Wisconsin.
Disappointed not to see John Martin in the video, but I know he's very busy. So, you are correlating some of these data with your aerosol data with data from radars that are satellite mounted, and I understand that you're a NASA biased person. So, but why not use like WSR 88D data, which is going to have a lot better coverage near the surface, and particularly in the layers where you're going to have things like convective boundary layer, Bragg scatter, that can actually tell you about where those aerosol layers might be
That's-
concentrated?
Yeah, that's the direction that we're going at. And actually, I was talking to Angela Rowe and Tristan Lacouillet about that.
Yeah.
Yes, because I understand yes, so I'm biased. I come from NASA, so I'm very familiarized with NASA products. But there are certain limitations with the retrieval and yeah.
Okay, understood.
That's a great suggestion, so I really appreciate it.
So I just have one more. Just wanted to clarify that, that you're not necessarily suggesting that there's a causative mechanism between the aerosol transport and the formation of tornadoes, right?
No,
Right,
no.
yeah, that it's strongly correlative.
It's
and that
strongly correlated.
Yeah.
Yes.
And a lot of the examples that you showed, particularly from 2011, those are strongly synoptically forced outbreaks in which the warm sector has strong southerly flow happening at around 850 millibars,
Yes.
hence, Herculean aerosol transport that's happening just at the same time that an outbreak is happening.
I actually had this conversation with another colleague of mine too, because that's something that we need to take into consideration. And the reason why we looked at so many other cases outside of 2011. Particularly, and again, this doesn't necessarily relate to tornadoes, because there are other things to take into consideration. But we looked in terms of radiative transfer. We looked at other cases, for example, for African easterly waves, where you turn on and off the aerosol, and that there you see the effect.
Okay.
So that's something that we hope to do, is to be able to run experiments like that, where you actually can remove completely the aerosol impact and then, or add it using a model. Yes.
Okay, great, thank you.
Video. Could you say a little bit more about the inputs in terms of you're getting aerosol profiles from Mayra? What are the uncertainties in those profiles, and how do you know how good they are?
That's a great question. So in terms of uncertainties, well, I can give you a feel about what's probably potentially wrong with them, and definitely the vertical is an issue, because aerosol models use sources and sinks, and sometimes we have a simulation for vertical sensors from space, like Calypso. And the problem with Calypso is that overpasses are every 7 to 8 days or so, and for modern data, it's not even flying anymore. So yeah, I would say that in terms of the vertical profiling, that's a big thing that we need to take into consideration. And the reason why I'm trying to collocate some of these events that are closer to Wisconsin, where we actually have the HSRL data. And the purpose of that is, obviously, with the HSRL, you get higher resolution and more accurate observations, but at the same time, you can validate or look at the model and tell a story about how good or bad the model is doing.
In one of your early slides, I believe it said that aerosol loading could increase surface heating. How does that happen?
It depends on the aerosol type and of where in the aerosol. So let me go back. Here we go. I don't know why my cursor disappears. So, right, that may be the mechanism, right?
Yeah, well, there was an earlier one where there was an explicit statement, but yeah, I don't. Maybe
Yeah. So technically, this is it. So here you get heating associated with the aerosol layer, and in this particular case, is by absorption and where it is absorbing in the atmosphere, the aerosol type, and the chemical composition of the aerosol. So it depends on the type of aerosol, because if you have a more absorbing aerosol and it's higher up in the atmosphere, something like this will happen, where basically, yes, you're going to get some of your electromagnetic or solar radiation actually coming into the layer, but a lot of it is going to get absorbed before it hits the surface, so it acts at that boundary.
Okay, by surface heating then, do you mean a surface layer instead of the surface itself?
Yes.
Okay.
Sorry, yes, that's true. So
Yeah,
it would be.
because-
I'm not specifically talking about the ground,
Right,
but the
that's
layer
what-
above the
okay,
surface. Yes,
okay.
yes.
Yeah, because you wouldn't expect any reduction in the actual ground surface heating.
Yes.
Okay.
Yes, yes. Good point.
And along those lines, just so to clarify, it seems to me when you have a high smoky day, the surface doesn't heat as much, and so the surface boundary layer temperatures are cooler, actually.
Yes.
There could be heating in the atmosphere, but the overall impact on the surface temperature
Yes,
could
and
still be cooling, correct?
And that's an excellent point because, and I didn't mention this, but it's an excellent point, and thank you for bringing it in. I think that the other aspect is the aerosol loading, and if, my hypothesis is that there's a critical amount of aerosol that you need to have to see these effects, but if you have a lot more, then exactly what you are mentioning is what's happening. And we experienced that last year, and I'm pointing at them because that's exactly what happened to us. It was, and that's what I was trying to show with the radiative transfer. We know from the observations that it was hot aloft. It was June 30th in Madison, and we were wearing jackets because it felt a lot cooler in the surface, or near the surface, yes. Excellent point.
Well, I know I have more questions, but we'll hold questions to some discussion out with coffee and snacks, and let's give Mayra another round of applause. Thank you so much.
Thank you.